Hello and welcome. In this video, we're going to take a look at a type of problem called a linear programming problem. Now, it's called a linear programming problem because all of the equations and functions we're going to be dealing with are going to be linear functions or linear equations. And programming problem, well, we can kind of find out that there's a very programmatic way to be able to solve this kind of problem. But in this video, let's take a look and see what kind of a problem we have when we're dealt with a linear programming problem. Well, a linear programming problem will involve two components. We have an objective function, and that will be some sort of quantity that we wish to maximize or minimize. So if we want to think of an example of something to be maximized, we might be thinking of profit. If you want to think of something that we want to be minimizing, perhaps we're trying to minimize something like cost. Now, the other part of the problem are going to be various constraints. And these constraints, they're criteria that we have to obey, and those are going to be in the form of linear inequalities or linear equalities. Something where perhaps the sum of certain values cannot exceed something. That kind of idea. Let's take a look at an example and see how we can get some linear inequalities that describe constraints and a linear function that describes some objective. Okay, here's an example. Suppose we have a company that manufactures Sleep Ease mattresses, and they have two manufacturing plants. Let's just call them Plant A and Plant B. Now, Plant A has 50 mattresses in stock, and Plant B has 60. Now, the mattresses need to be shipped to their warehouses, and it will cost a varying amount to ship each mattress from one plant to one warehouse. We have a table here. Plant A to Kelowna is $80. Plant A to Penticton is only $50. Plant B to Kelowna is $100, and Plant B to Penticton is $60. So right away, you can kind of see that we probably want to keep our costs down as much, and Plant A is a little bit cheaper. Now, Kelowna needs 40 mattresses, and Penticton needs 30. How many should be shipped from each plant to each warehouse in order to minimize the cost? It's pretty obvious in this case that this is a minimization type of problem. We want some sort of quantity to be as small as possible, and that quantity is cost. So we can make some sort of objective. And you can also see that there are some constraints for this problem. Well, first of all, there's only so many mattresses in each plant to be able to ship. And we need to somehow divide those up into Kelowna and Penticton. And we can't just invent new mattresses, so we'll have some sort of constraints there. It might be best to try to come up with what our variables are. And it seems like there are 4 different variables at first glance. With Kelowna, Penticton, and 2 different plants, there could be 4 different ways that a mattress could travel. But we can actually turn this into a 2-variable problem once we sort of visualize it. Now, first, we can imagine Plant A as having 2 options. A certain number of mattresses will be sent to Kelowna, and a certain number of mattresses will be sent to Penticton. So why don't we at least use a couple variables, x and y. Now, we also have our second plant. And rather than create 2 new variables here, if we know that Kelowna needs 40 mattresses, by knowing what the value of x is, we can already determine the value of the number of mattresses being sent from the other plant. We will never send more or less than 40 mattresses if we're going to minimize cost. The constraint here is we have to have 40, but we don't want to provide more because we're minimizing cost. So the number of mattresses that will be sent from Plant B to Kelowna is simply going to be the remainder, 40 minus x. The number of mattresses sent from Plant B to Penticton is simply going to be the remainder, 30 minus y. So we only have a 2-variable problem. Okay, well, now that we've got the variables figured out, it's time to think about the objective function. Our objective function in this case is to minimize cost, so we'll let C be our value to be minimized. And looking at the table above here, we can form a nice equation with $80 per mattress shipped from Plant A to Kelowna, which we've indicated as an X. And we can indicate $50 times Y for the total cost of shipping mattresses from Plant A to Penticton. And then, of course, multiplying $100 per mattress shipped from Plant B to Kelowna and $60 multiplied by the number of mattresses from Plant B to Penticton. Now, this isn't exactly in a standard form. We should be able to collect a lot of terms here by expanding this out, and we'll see a nice linear equation in x and y. And there we have our cost function. Cost is $5,800 minus $20 per x minus $10 per y. But what are our constraints in this case? Well, we've already set the problem up so that we ensure that Kelowna receives precisely 40 mattresses and Penticton receives precisely 30 mattresses. But there are some hidden inequalities here. Well, first of all, the number of mattresses shipped from plant A to Kelowna, which we've called X, it can't be a negative number. It has to be a positive amount. I mean, if we could make it a negative number, imagine the cost savings. We could just receive mattresses instead of sending them, but that really wouldn't make any sense. So we would have to put at least a constraint in there that x and y both must be greater than or equal to 0. Now similarly, the number of mattresses sent from plant B to Kelowna or Penticton must also be positive numbers. But in this case, it's not simply just having x greater than or equal to 0 and y greater than or equal to 0, we must have 40 minus x greater than or equal to 0 and 30 minus y greater than or equal to 0. Now, it may be worthwhile taking these last two constraints and getting them into a more standardized form where x is isolated. So we could turn these last two constraints into 40 greater than or equal to x and 30 greater than or equal to y. And we can put all of these together so that we have cost is 5,800 minus 20x minus 20y, and then our constraints will all be in x's and y. Now let's take a linear programming problem and see how we might be able to turn this into more of a linear matrix type of problem. We'll specifically look at standard maximization problems. Now, a standard maximization problem is a little bit more specific. It's a linear programming problem where the objective function is to be a maximized value. All of the variables involved in the linear programming problem are assumed to be non-negative, and also importantly, all of the constraints are linear inequalities, where we have some sort of linear expression of the variables where that quantity is less than or equal to some constant. Let's just see an example. In this example, let's suppose we wish to maximize profit. Let's suppose that for each x, we get 50 units of profit. And for each y, we get 60 units of profit. And let's suppose our constraints are also linear. The total number of units x plus y cannot exceed 70. And perhaps we have some other constraint that 4x plus 5y cannot exceed 300. Now let's assume, of course, that x and y are greater than or equal to 0, that these are only positive values. What we can do with a problem in this form is we can actually turn inequalities into equalities by adding something called a slack variable. Slack variable is essentially if we don't take up all of a constraint, since we can be less than or equal to 70, there might be a little bit of room left. Suppose our optimal solution is that x is 30 and y is 20. Well, that would only be a sum of 50, leaving us with 20 additional units of slack. And so our slack variable will just take up that space. So let's see, our first constraint, x plus y less than or equal to 70. Let's add a slack variable, call it u, which is how much room we have to spare. And now we could think about some positive value x plus some positive value y plus the amount of room left equals 70. And u is also going to be some non-negative value. In our second constraint, we have 4x plus 5y is less than or equal to 300. Again, we can turn that into an equality. 4 times some positive number plus 5 times some positive number plus possibly a little extra room to spare is equal to 300. But we've already introduced one slack variable for the first inequality, being how much of the 70 is not being used. We can't use the same value again. We'll have to use a new slack variable, and maybe we'll use v in this case. Now we have our constraints in the forms of equalities, and we know that x, y, u, and v are all greater than or equal to 0. They are all non-negative. Now, our profit is an equation, and our constraints are equations, and they're all linear equations. And so you can imagine where this might be going. We have a whole system of linear equations, and we can put this into a matrix form. Now, this is a very special kind of matrix. It's not just an augmented matrix. We call this a tableau because it does have variables, it has constants, so we'll put a vertical line between the variables and the constants. But we also have one particular equation that's different from all the others, and that's our profit equation. It's treated differently than our constraints. So we have a horizontal line separating our constraints from our profit. Now, as a tableau, we have several variables now because our initial variables were simply x and y. But we've added additional slack variables, u and v. Now, it may not initially seem like a variable, but profit is dependent on the values of x, y, u, and v. And so profit is also going to be a value that is variable, depending on the others. And last but not least, we have constants. So we'll add a vertical divider and we'll put our constants at the end. Now let's take a look at our first constraint. X plus y plus u equals 70. 1x, 1y, 1u, and 70. And our second constraint, 4x plus 5y plus v equals 300. So 4, 5, 1v, and 300. Now make sure to put some zeros in there wherever a variable does not show up. Now we don't have any more constraints, so let's put a vertical divider in to separate the constants and a horizontal divider to separate constraints. And last but not least, we have to do a little bit of rearranging on our profit function. Taking a look, profit is equal to 50x plus 60y. Now we'll do a little rearranging to get 0 on the right-hand side and subtract 50x and 60y from the left. Negative 50x minus 60y plus p equals 0. And so on our last row, we'll have a negative 50, a negative 60, 0 for both of the slack variables, 1 under profit, and c for the constant. And then we can finally finish up our brackets for the matrix. And this is called a tableau. More specifically, we call it a simplex tableau. And we'll be taking a look at the simplex method shortly in another video to find out how we solve this. But it's important to know how we rearrange everything in this table. So our x and our y, we will call these our basic variables. We also have our u and v next, and these are the slack variables. And u and v on their own don't necessarily show up in our objective function, but they will help us to determine the overall value of the objective and also determine how much of each constraint is actually being used. The first few rows are going to be our constraints, and our very last single row is the objective. And as we go through the process to solve for the optimal solution, keep in mind that we always assume x, y, u, and v, all of the variables are greater than or equal to 0. Now it's going to come back to the idea of pivoting around a single entry in a table. That's going to be a major part of the simplex method. But first we need to determine what is the solution going to look like? What is feasible? And that's not just necessarily just like solving a system of linear equations into reduced row echelon form. The simplex method is going to be a little bit more interesting, trying to find out which of the variables is going to make the biggest impact on our objective function but still be feasible. Now we'll save that for a future video on the simplex method, and then we can also, in the future video, take a look at how we can maybe put this information into software such as Excel and use a solver for many multivariable problems. But we'll save that for later. Thanks for watching, and I'll see you again in the next video.